of Bob. I think you've already heard that. I would like to mention that last week's lecture, which I was here for, and we recorded, the recording didn't come out. We had a technical difficulty. So that one's not going to be online. Today will be recorded, of course, as we normally do, and the very first one was. But Bob has graciously agreed to come back at a later date and redo the lecture from last week. And we'll let people know in case you want to come and be a small mock audience.
We'll have the applause at the appropriate locations.
So that way we'll have it recorded. But it would be really nice to get all three of these recorded, so we will do that at some point. And with that, I'll just turn it over to Bob.
Thank you, Mark. So when I was reviewing these slides with my co-graduate student and now UNH professor, Jim Ryan, he thought that since things are always somewhat doubtful about theories from things so far away, I should put in an image of Rodin's The Thinker, so I found this robotic version to start with. So the first lecture I talked about the life of stars. Actually, some of the stars, you may recall, actually occurred shortly after the Big Bang, the first couple 100 million years. Where hydrogen was accumulated, large stars came, and actually a simple radio experiment with just 5 people out in the outback of Australia managed to see the remnants of the 21 centimeter radiation highly redshifted. So it's nice you can do an experiment with only probably a few $100,000 instead of hundreds of millions. And we talked about some of the stellar endpoints, white dwarfs. And if they're in binary systems, you end up with nova, and some types of supernova, and then more massive stars, different type of supernova, and then you end up with neutron stars, pulsars, and black holes. Last week, I talked about the discovery of gamma ray bursts. I'm going to recapitulate, since I realized we didn't have a recording to refresh your memories, some of the major outcomes of the first 30 years of measurements. Things happen kind of slowly occasionally in astronomy, so I'll recapitulate some of that history, and I participate in part of that. And then today we're going to talk about the theories of gamma ray bursts, what causes them, and also extend into multi-messenger astronomy, which is getting information from objects other than by electromagnetic radiation, namely by gravitational waves and by neutrino measurements. And that also relates to some of the measurements that have been made on gamma ray bursts. So I'm going to start out by saying how these gamma ray bursts were discovered. So back in '63, JFK put up agreed with Russia to have a nuclear test ban treaty, no atmospheric tests. And so this is like trust but verify long before Reagan. Darby came up with a plan to put up satellites, civil satellites, to look for possible atmospheric tests by the Russians. And the idea was to do it by triangulation, by having multiple satellites, looking at the arrival time of X-rays and gamma rays from these blasts in the atmosphere, to triangulate and find out where they were on the Earth's surface. Did this for several years. Well, in 1967, they found bursts that were coming from other than the Earth's surface, somewhere off in space. And they were classified for 6 years, because well, perhaps this is something the Russians were doing, launching rockets into space and trying to hide their nefarious activities. But they realized that wasn't the case. There's some kind of a natural astrophysical process going on causing these brief, they only lasted a few seconds, blasts of gamma rays. And they were announced in 1973. I was in graduate school at UC Riverside at the time, getting involved with the gamma ray experimental group flying high-altitude balloons. So it's a very exciting time for us when we can go make some measurements. If these fist-sized detectors on a Vela satellite could be seeing once or twice a year, seeing these bursts, maybe if you flew something that was 100 times the area or 1,000 times the volume, maybe on a daily basis, because it looked like it only lasted about 1 to 3 days, maybe have a chance of detecting these. Now, it was a bad time for the group because 2 years earlier, against the vociferous objection of the leader, Steve White of the group, they cut down a payload through a big thunderstorm. The parachute got emptied, and it free from 30,000 feet was totally destroyed. So we're in a rebuilding period. It took us until 1975 to be able to do another balloon flight. And while we set an upper limit, we didn't see any, but it was very exciting that we had a chance to maybe go make some measurements in the gamma ray burst. So this is by high altitude ballooning. I got a picture of a launch here, which I'll show this. It only lasts a minute. Always very exciting because you're hoping for a good outcome. The parachute is always extended because at the end of the flight, you cut away the balloon and the package drifts down. it takes about an hour to inflate the balloon. Of course, you hope there's no ground winds. This is a very perfect launch with no wind. You'll see that the crane has to actually back up to do the release.
Colors away.
The excitement is because it doesn't always go that smoothly. In the previous talk, I showed an example of a case where there was a problem with a release in Australia. You know, if the package of the balloon is out in front of you and you release the balloon, it swings down and hits the ground, and it can scrape off your antennas. So you're hoping to transmit telemetry through the whole flight. But once the antennas are gone, your goose is cooked. You can't do anything. This is a picture from low altitude. You see when you're launching the balloon, you're down at 1,000 millibars pressure, atmospheric pressure. And this is going up 25 miles where it's only 3 millibars pressure, and the balloon expands to the full diameter. And the balloon doesn't contain the pressure. It's only 8 mil plastic. And so at night, when the atmosphere cools off, the balloon tends to fall down, and you have to release ballast to keep it from going deeper. You don't want it deep because it cuts off your gamma ray measurements. And the next day, when it heats up again, it goes higher than before and gas leaks out. So after about 3 days, you have a package of maybe 1,500 pounds, equal amount of ballast. After about 3 days, you have to end the flight. One quick story. So I got to go on some balloon recoveries. They send planes underneath to track the balloon. At the end of the flight, I'm a green, a graduate student, so they say, can you see the package? You're looking at something up 25 miles up. It's kind of hard to spot. Oh, yeah, I finally see it. So you give the cut down command, and it starts falling. Of course, there's no air to speak of. So it falls for many minutes as though there's no parachute because there's no air up there to slow it down. So the pilot says to me, of course, looks like a free fall to me. You get my heart rate going, So after about 10 minutes, you start to notice, you see two things. You see the balloon falling, because they ripped the balloon, and your package falling at the same rate. And gradually, the balloon falls faster than your payload. And so they just have fun with new graduate students. So these gamma ray bursts take place at random times, random locations. That's why it's so hard over time to get many observations, because you can't take a focused telescope. First of all, you can't really focus gamma rays. They go right through your instrument. So you have to have good fortune to collect information on a gamma ray burst. We used to say, once you see a gamma ray burst, you've seen one gamma ray burst. They're all unique. You give information to theorists. Every burst looks different. The time scales are from tens of milliseconds to hundreds of seconds. You see some common behaviors. Occasionally you'll see, we call these fast rise exponential decay. You'll see families of things like this, but such a variety. The time history doesn't tell you a lot about what's going on. It doesn't lead right to a theory. The spectra are principally in the gamma ray range. At the lower energies, from 20 keV to a couple hundred keV, it doesn't fall away very fast. You call it a hard spectrum because as you go up in energy, you don't have much of a decrease in the intensity. And at higher energies of about a few hundred keV, it drops more rapidly. It's a steeper spectrum. You call it a soft spectrum. So then after I got through graduate school, I went off to work at Marshall Space Flight Center. It was lucky for me because they had their experiment selected to be in the Gamma Ray Observatory. It's one of the great observatories that NASA had planned to take advantage of the space shuttle lift capability. And this shows you a bit of, so our goal was to see, where are these bursts located? And if we do the location, you can see these are tipped. These are 20-inch diameter detectors. They have crash padding on top in case we roll over into the flight. So you can imagine if you had a burst that was directly overhead, you get equal counting rates because you have equal exposed areas each of the 4 detectors. But if a burst is over, I can't point that direction. If you see it coming out of the board, normal to the one detector you see in front, you see almost entirely a large area exposed here, but nothing here to the other detectors. By looking at the relative counting rate of the burst in different detectors, you can get a direction good for a bright burst to within a few degrees, and for a weak burst, maybe only 10 or 15 degrees. And the goal of the BATSI experiment, burst and transient source experiment, was to map the sky. So the question would be, are they from our galaxy? Do you see like a Milky Way distribution, the plane of the galaxy? Or are they from somewhere distant in the early universe and you see something like the cosmic ray background radiation? Are they coming from every direction equally? That was our goal of the mission. We didn't know at this point it would be 10 years to the launch of the experiment, partly caused by the Challenger accident, and partly just by the technical difficulties of us and other experiments to complete the job of building it and testing it. So the state of knowledge just before launch of the Gamma Ray Observatory was this. You can see there's some small squares of a few square degrees that have been observed, but a lot of these things are timing arcs for two satellites, one maybe near Venus, one near the Earth, would see a gamma ray burst, and by the relative time of arrival, you can draw a circle on the sky that shows that somewhere on that circle. It's a pretty fine circle. You don't have much width to the circle, but you have no idea where in that circle it came from, just the relative time delay because of the arrival time of the burst at each of the two experiments in different satellites. And so we had a conference shortly before the launch of GRO where we gave out badges to people they could put on. It said cosmological or galactic, and it was about 50-50. So really nobody knew before this. And so that was the launch in 1991, April 1991. There's 4 instruments. I won't talk about the others, but you can see we have 4 detectors on the top and 4 on the bottom. And the faces are parallel to the faces of the regular octahedron. So we view the whole sky equally, except for what's occulted by the Earth. I used to know where that was on the Earth, but I couldn't look it up again. There's a couple small features. If you spend a lot of time looking, you'll see where it was. Not that it matters. And so after 9 years, these are the results, and you can see it looks very much like the cosmic ray background, microwave background. This is a map of the entire sky, equal area. So this is plus 90 degrees latitude, minus 90 degrees latitude. The galactic center is at the center of the plot. This is west longitude 180 and east longitude 180. At this point, that point are the same point. So within a percent order or so, you're seeing them come equally from all directions. So it's highly suggestive they may all be coming from the deep early universe. But I'll talk about that more in just a second. Now this is a complicated plot here. Let me describe this. So first of all, because we'd only been up for a year, we couldn't see bursts that occur only once within a 10-year period. So this is log of n, the number per year. So log of 1 is 0. So if you're seeing 1 burst per year of a particular intensity, this is how bright they are. These are the really bright bursts, like 1,000 photons per centimeter squared per second. This is 1 photon per centimeter squared per second. And so you ask the question, above a certain brightness, how many events have I seen? Now, if you think about bursts, they're close to you, and so bursts that are very bright in a certain radius, you have a certain number that you see. As you go to weaker and weaker bursts, you're going to larger radii. And so the number you see goes up according to r cubed, 4/3 r cubed times the density. But as you're going further away, they're getting dimmer by 1 over r squared. So you get a minus 3/2 power law that you expect. Now this is the weakest burst that BATSI can see, down where it says BATSI limit. And what is striking here is, once you get down to this level, if you ask how many bursts do I see, you don't see any more. For that last factor of 10 in sensitivity, there aren't any more. So with our small detectors, we're seeing this distribution. We're seeing all that there are. We're seeing the boundary of the distribution. So it's very suggestive we might be seeing events from the early in the universe. We don't know for sure yet. We don't know the distance, but we know we're seeing all of them with our detectors, which is quite an amazing result. So then in 1997, another satellite, Beppo-Sachs, able to see in the hard X-ray range a much better angular resolution to arc-minute accuracy, managed to see a burst and look 3 days later and see it was dimming. And so, of course, there's 2 points. As you see something now much beyond just 100 seconds, days later you see it's cooling off. You're seeing the dying ember of this gamma ray burst. And also because of the good positioning, there was a Dutch astronomer, X-ray astronomer as well, Jan van Paradijs, who sadly died just 2 years later at the age of 53. He managed to get some telescope time at a La Palmas telescope in Canary Islands. And they got these images in the optical, and you can see a few days later, February 28, a few hours later, 21 hours later, you see a black dot in negative image here, and 3 days later it was gone. And they actually looked with this area with the Hubble Space Telescope about 6 months later. They could still see the remnants of the burst, and there was a galaxy behind it. Now, it was too dim to get a redshift measurement to get a distance, but 3 months later, another burst, they got lucky, and they were able to see that the redshift was about 2, it was like 8 billion light years. So finally, now this is 30 years after discovery, after 30 years, we finally know the distance scale of these objects. And that means that they factor the brightest explosion, the most energy explosion in the entire universe. About at least 10 to the 51 ergs, maybe 10 to the 53 ergs. The sun puts out 10 to the 33 ergs every second. And the sun puts out, in its whole lifetime of 10 billion years, about 10 to the 50th erg. So this is more energy in a few seconds than the sun puts out in 10 billion years. So it's kind of a dramatic amount of energy in a short time, a lot of power. So now we're going into new material. So something else we learned with BATSI was to look at the histogram of the time duration, the duration of the events. So there's two bumps here. There's a 0.1 second bursts, quite a few of those, maybe a third of the bursts are only about a fraction of a second. And then you have a long burst. And theorists at the time, Martin Rees in particular, suggested this might be a time scale that neutron star mergers might be the source of this class of burst. And there's more to say about that later. And the longer burst, people weren't sure what was actually causing that. So what are the key observational facts? Because the bursts have variability less than a millisecond, that implies the light travel time across the area producing the output. They're very small, less than 10 to the minus 4 of the sun's diameter. So it suggests it might be a stellar mass black hole or a neutron star. So the size of the region emitting is very small. And the measured energy release, now that we know the distance, we know how much energy, it's as though you converted the rest mass of the sun entirely in a few seconds. That's the amount of energy involved, or at least maybe a percent or tenth of a percent if it's beamed. So we're seeing the emission coming to us, but we don't know what's happening in the rest of the 4 pi steradians and the rest of the, we only see one small measurement because it's coming at us. But what's happening in the rest of the sphere it's emitting into, it could be blank or it could be full. We just don't know because we're stuck viewing from one location, of course, our location. I got to throw this in. This has got to be the only cartoon involving gamma ray burst ever produced. It says, despite funding cuts, research into the origin of gamma ray bursts continues as best it can. If only we could do experiments. We're observers of what's coming our way. And of course, we get fortunate, as you see later on in the talk, of being able to get some information besides just the electromagnetic radiation. But we're stuck here. I used to be very jealous of people in the lab. They could go in the next day and turn some knob and make some new measurements. All we could do is see what's coming our way and try to make sense of it. That's what theorists try to do. So these are the principal theorists that have been active in trying to explain gamma ray bursts. You might recognize one name, Martin Rees. He's written about 10 or 11 books on cosmology. He's the Astronomer Royal in England. He's been there since 1995. He's quite an important figure in astronomy. The other name, I don't think you know the other people's names, Donald Lamb. Well, first I should mention Bohdan Paczynski. There was certainly a point before GRO was launched that the only theorist that thought that it weren't some kind of galactic phenomenon was Bohdan Paczynski. He's at Princeton. So it's very clear you don't decide things in science by a vote, by democracy. It's an interesting process. You grow up in science, you see how it works. You have people with theories, you throw up data, you have lots of discussions, but it turns out occasionally it's the one lone voice that has the right view of things. You have to let the process run. So Donald Lamb had the opposing view. He's a principal theorist that thought it was some kind of process involving neutron stars in our galaxy was the source. So it has to be some place where you go down to a very small object, get a lot of energy from the gravitational field to get these kind of scale of energies. So it's something small. So that was not a reasonable thing. He pursued those theories for 20 years with dozens of graduate students, a very honorable, decent process to go. Nobody knew at that point for all those years what was going on. Stan Woosley did a lot of work besides UC Santa Cruz was modeling nuclear atomic explosions. He worked for Los Alamos for many years. I'm sure that was his day job. He surely much preferred studying astronomy than studying the details of nuclear explosions. So in 1995, there was a replica, really, of a very famous debate that took place in Baird Auditorium at the Smithsonian Natural History Museum. Back in 1920, the issue was, how far away are these spiral nebula? Mount Wilson's getting all these images of these spiral nebula, like Andromeda, for example, and nobody knew the distance scale. It's another distance scale kind of a question. And Shapley believed they were fairly local. I must say, one thing that really struck me when I was first taking astronomy was reading in the astronomy book that the size scale, the angular extent of the Andromeda Nebula is 4.5 degrees in the sky. So that must be a typo. The moon is 0.5 degree. You know how far away that is. And this Andromeda galaxy, it's 2.5 million light years away, is 4.5 degrees. That's just an amazing fact. And so people thought that was kind of too much to believe. You know, so many astronomers of the day thought these spiral nebula were some kind of local phenomenon near our galaxy. And the other person, I forgot his name now suddenly, Curtis, thought that they were in fact very, very distant. And this wasn't resolved until the work done primarily by Hubble 9 years later. Well, so they had this debate. It was moderated by Martin Rees and Bogdan Paczynski, my boss at NASA. Jerry Fishman, the PI of the Batsy experiment on Gamma Observatory, presented materials in advance of the session, and they debated it. So at this point, we already have the data from Batsy showing we have isotropy. These bursts are coming from everywhere. So theorists don't give up their positions easily. So his position was that there may be neutron stars that were in binary systems, and they get disrupted, and the neutron stars get sent out at high velocity away from the galaxy and form a giant cloud around the galaxy, a spherical cloud, and that's where the bursts are coming from. And so the edge of the distribution is the edge of this cloud of neutron stars that are still part of our galaxy. And the idea was at that point to have a more sensitive detector, and you might start seeing gamma ray bursts from the Andromeda galaxy. Well, of course, it turns out that wasn't right. So let's talk about the models. Most models involve the collapse of a massive rotating star forming a black hole, or neutron star mergers for the short bursts. Rotating accretion disks are formed. I talked in the first lecture about conservation angular momentum. There was a famous mathematician, Emily Noether, German, that had very poor treatment in her academic career. She couldn't get tenure. She didn't get paid for her work. She had to audit her classes in college. But she met some very famous mathematicians, Minkowski, David Hilbert. When she died several years later, she was Jewish, so she was forbidden from teaching in 1933 and came to the United States. And when she died quite early at 53, then Albert Einstein wrote an obituary for her in the New York Times, saying she was the most important female mathematician since the education of women began, which means that I guess that didn't start very early, very sad state. But she understood the reason for the conservation of angular momentum was because of symmetry. It's a very important thing. So the mass can only escape out of the axis of rotation just outside the event horizon, where beyond the event horizon, everything is contained within the black hole, producing jets at very high speed. I'll show some images of some modeling here in a short time ahead. And these jets that form are typical in other domains like quasars and radio galaxies. This is just theory. We're sitting here a distance away. This is just not provable, but it seems like very likely. So the collapsar hypernova model actually started with Stan Woosley. The bursts are found with an exception in systems with an abundant recent star formation. And there are several cases where a supernova is followed immediately after the gamma ray burst. And it may be that most gamma ray bursts occur too far away for a supernova to be detected. Of course, there's always exceptions. So if there's some bursts that are nearby, but the supernovas aren't seen, well, maybe they're swallowed up by the newly produced black hole. We're stuck here with, you're looking for patterns, and you just can't find universal behavior. So you're looking at many cases trying to come up with a model, but not all the data you look at fits all the ideas in a model. That's what life is like as a theorist. The energetics, we know the distance, and so we know how far they away. We know they make as much as 10 to 53 ergs, a time scale of seconds. That's the output of the sun in 230 times the age of the universe. And if it's beamed, it's 10 to the 51. So it's still a huge amount of energy. So this on one slide is the idea from both the hypernova collapsar model and neutron merger model. So I'll read it up first from the bottom. If you have a massive star where you have iron at the core, and you can't get more energy by going to higher atomic number than iron because it takes energy to do that, the iron actually absorbs photons and collapses in a matter of seconds. You also have neutrons form from combining high energy protons and electrons emitting neutrinos. So in a matter of seconds, you end up producing a neutron star. And things are collapsing, and probably it's just like a figure skater pulling their arms in, rotation is starting. So you have an axis forming. So that's from the bottom here, you're heading toward the central engine, a black hole, with rotation. We're kind of turning 90 degrees here. The rotation axis is here. For the short burst, you have two neutron stars merging, forming a black hole because there's more than two solar masses. That also has rotation built into it because of the in-spiral of the two neutron stars. So in both cases, you end up with a central engine. It's not like you can have a good model of this. This is just something that the modeling starts when you say, I presume I have a lot of rotation and I have gamma rays being emitted from that point. You can't really penetrate the details of what's actually happening in the central engine. But the models show that you have very, very high energy particles, and some of the particles are moving faster than others. And blobs can actually overtake solar blobs and cause collisions and produce gamma rays. So there's what's called internal shocks producing gamma rays. Eventually, this is the star boundary way out here. So we're inside the star, the massive star. Eventually, you hit the external medium. There's material outside the star. It might have been from a wind already emitted from the star. You start encountering external material, and you end up producing external shocks. And I'm showing a short movie of this. So there's the star, jets being put out. You see the collision's about to take place here, and you get brightening. That's an internal shock. And then the external medium is being hit here. So this is the idea of the model. The other thing to explain, once we started seeing good positions for the burst, and we see emissions in other than just a gamma ray range, you started seeing long-lasting afterglows. This is in the X-ray range, and you're seeing emissions. There's the actual burst itself, but they last for a long time, and you see these slope changes. You see it stays at one certain level. This is a log-log plot, so this is a power law. But the power law index changes. There's these slope changes. What's causing that? Well, the theorist has dealt with that. So the actual energy in these blobs going out, they think they have gamma factors multiplying the energy. You have E equals gamma mc squared. You see that right here, of up to 200. And the angle, this is a relativistic effect, the angle that you see this in is like 1 over gamma. So if you have a gamma of 200, you're only 1 part in 10 to the 5th away from the speed of light, even though it's a massive particle, very, very close to the speed of light. And the angle of emission that you can see is only 1/4 of a degree. By the time it slows down to a gamma of 2, you're 87% the speed of light, and you can have a 28-degree emission cone. So here's what this looks like. This is also due from a Stan Woosley paper. So at the source itself, you have a fairly wide opening angle, maybe 35 or 40 degrees. But in the early part of the afterglow, because it's such a high gamma, they're showing a gamma of 100 here, maybe only be able to see about a 1/2 degree portion of the jet. Of course, we've moved the Earth a little closer than in reality. So so you only see that portion. So you're gradually, because you're encountering other material, slowing down the particles. So gamma is decreasing. The particles are slowing down. And so you get to a gamma of 50. When you get to a gamma of 10, you actually have an opening angle wide enough that you start to encounter the actual edge of the jet. And so when you go to lower gammas, you don't pick up any more emission because you've seen all that there is. And that's where you see the slope change, and that's the model. Of course, there's mathematics behind all this. It's in a talk like this, we're not going into the equations, partly because there's no time. Of course, I'm not really knowledgeable about them, either one. So these are some still frames of a movie I'm going to show here. You can imagine this has only been possible in about the last 5 years. They have computers fast enough, supercomputers, to do this. So this is a case where if a jet reaches the surface, you can have a gamma ray burst. The colors here, this is the density in log scale of the grams per cubic centimeter, up to 2, that's 100 grams per cubic centimeter, down to very, very low density, 10 to the minus 5th. And this is after about less than a second. You start to get this cocoon phase. Most of the motion of the jet is penetrating out towards the surface, but is expanding some width. They call this the cocoon. After 3 seconds, you're starting to get
is a very low density in the middle, you can actually have gamma rays coming from the very central portion of the star being emitted and of course finally getting to us. Now, another possibility is the jet dies out. So in the modeling, they just stop the production of energy coming from the jet after a few seconds. So they actually turn off the jet here after I think it's about 2 seconds or so, 3 seconds. So there's no driving force behind the jet, but there's still a lot of momentum in what's been sent out before. So then the jet slows down, but it can still reach the surface, and you still have so you got this very low density area, 10 to the minus 4 grams per cubic centimeter, that you can have emission of gamma rays. And I'm going to show you an example. They believe they've seen an object just recently, just in the last week it's been published. So when you finally get to the end of the process, after 5 seconds, you have the ability to have gamma rays coming out in maybe a cone as wide as 15 or 20 degrees, not just the dark blue, but the light blue areas have densities low enough that gamma rays could escape. So this is not an artist's conception. This is very detailed modeling that's been produced for a paper. So here's the movie if the jet source continues. So we're going to look at the 0 on the plot. You'll see the jets start to begin here. See the cocoon widening up, getting very low density in the middle, expanding out. And we'll do the case. So they'll pause this several times at different densities. The jet turns off and when it gets choked. So I'll run this movie. And so this time is increasing a lot more. It's taking more time for this to reach the surface, around 19, 20 seconds. And the gamma ray is able to get out in that last portion when we're in the 10 to the minus 5 zone. So in a case like this, you have some emission of gamma rays as the jet cocoon reaches the surface. But we don't have this column of low density area in the middle. So we have just a chance for a very small gamma ray burst. It may be, since we see a lot of supernova, but we don't see many gamma ray bursts locally. So it may be what's going on here. The rare supernova that produce gamma ray bursts are the ones that for some reason this jet production process continues. But in most of the cases, that jet process never escapes the black hole. That may be the reason that gamma ray bursts are pretty rare. Yes? Pardon me? The color scale is the density of material. So in this case, right now it's the density, so it's 0. It's like 1 gram per cubic centimeter. The reddest to the red is 1 gram per cubic centimeter. That's like water, right? And at the bottom here, its density is so low, it's 10 to the minus 15 grams, which is something certainly that gamma rays can penetrate. So this material of the cocoon that's expanded out here actually gets so thin that light can penetrate it. So it becomes transparent on that scale. So the first supernova that came shortly after gamma ray burst was in 1998 BW. It was found by a student of Glama, who was a student of Jan van Paradise, the one that first managed to find light associated with a gamma ray burst. And it's a very nearby burst. So the point is, so many bursts, the most distant gamma ray burst is a redshift of 9, very early universe. So although supernovae are bright, they're not so bright you can see them from the earliest times in the universe. So this is for many years, people had no idea what might be associated with a gamma ray burst. So this is the first case after 7 years after GRO was launched. There was an example of something that might be a supernova somehow related. This made great news in the community, which say maybe there's something related to supernova. So just recently as after the last lecture, there's a paper published by Izzo et al. In Nature, a fairly nearby burst, 163 megaparsecs away, found a very weak gamma ray burst. You can see this gray area is just the time when it reached its 10% of its total duration to 90%. It's a standard measure of duration, so you can ignore the gray area. So it's a very weak gamma ray burst, and they found suggestive things about a cocoon breakout. They found, I didn't show all the optical data here, but they actually find iron lines, lines of iron, only from early on, as though it's material ejected from the core. And very high expansion velocities, at 38% of the speed of light. This may be an example. Now, it's kind of like this in astronomy. You kind of look, you find an example of something, and you're saying that this is the model for cocoons breaking out of supernova, and that's what it is. But it's only one example. You have to be careful that this is clearly the right model because it's based on low statistics. But this is a tantalizing hint that maybe cocoons, jets shutting off, cocoons breaking out, that might be the association. So it's dynamics of what happens in the central engine of an exploding massive star that might relate to why some of them are supernova and some of them produce gamma ray bursts. But it's still early in the game of proof, I would say. Now this video unfortunately has no sound, but I'm gonna talk to the slides he shows. So sorry for the pause at the beginning. It had sound when I was at home. So there was a transient found in June, a very bright transient, optical transient. It has some interesting properties. And the next slide will show some of those right here. Very soon now. So it's very luminous, 10 times, 11 times the sun, or 10 times as bright as a supernova. And it peaked very fast. I mean, supernova take maybe 15 days and went up and down within just 2 days. It involves very dense material. Yet the power source stayed active for many weeks. He's going to show a slide here of the possibility of what this could be. This is the only one. It's a very unique object. Of course, it's called the cow because these random letter assignments happen to spell out COW. So it's hereafter known as the cow. Show your next slide, please. He said more than I did, I guess. This is a wonderful description at home. Okay, so one possibility, the second one, is an energetic jet from an exploding star. This looks a lot like what we were showing previously. So it may be, this is an example of what happens with a jet emitted from turns into a supernova, a collapsar, is this that the burst missed us. The jets are beamed in one direction, we may be missing the burst. So this isn't something he said, this is something that I recognize. This may be an example of the type of object that can produce gamma ray bursts. The burst just didn't hit the Earth. So this is another possibility that this is a white dwarf being gobbled up by a black hole. This one we can hear the sound on. Not that it's that important. There's the black hole. Tidal forces pulling it apart. What we need, of course, is more observations, more examples before we say the whole class of object like this. So it's interesting observation, but it's not definitive. So now we're going to turn to a different topic, multi-messenger astronomy. Yes, sure.
So is all that emission before it goes in the black hole?
Somehow, or what?
Anything that goes inside the black hole never results in anything that we observe. This is all material. When you have a black hole, and material is being drawn in very rapidly, it heats up before it falls into the black hole. This is all emissions outside the event horizon. Some of that emission will be directed and be consumed by the black hole. It's not part of what we can observe. Everything's shown here. That the plots I showed of the movies are all, you might say, at the edge of the event horizon, taking place exterior to it. The black hole is hidden just off the view of the videos, for example. So it's all exterior to the black hole, right?
What's the time frame for that video?
Well, there were two different. Seconds. Yeah, I showed some still frames that had the times in it. The one where the jet continues finished about 4.7 seconds after it started. So it's very, very dramatic and very fast. The one with the jet stopped, because there's no driving force behind the jet, it stops. I think that took place up to like 25 seconds before it kind of got to the surface where it was low enough density it could emit some gamma rays. And it finished, I think, 35 seconds in. Right. Yes.
Since we're recording the lecture, can you hold on a second? Let me get you the microphone.
Good. Bob, what does COW stand for?
It's just a random letter assignment.
Okay, so it doesn't stand for anything.
It stands for a cow. No, it doesn't.
Bob, now, are those jets parallel or perpendicular to the axis of rotation?
Parallel.
Okay.
Right.
Is the material in the jets, is that heavy material from the stars, or is it light material?
Light material, mostly electrons spawning in magnetic field lines.
Okay.
Not baryonic material. Right. In the models. Okay. Multimessenger astronomy is getting information besides electromagnetic radiation. So a simple example is like thunder caused by lightning. It's not very useful in that case, okay, but it's an example of getting information in a different channel. So we're going to talk about other channels that may occur in dramatic movements, changes in the state of a system, both neutrinos and gravity waves. And so, as I might not have said before, theorists are very adept, as they should be, at coming up with models for what might producing certain emission, but they need to be constrained by information. And if you can go beyond, if you just have a narrow range, like only looking in gamma rays, then it's hard. You can have many models that might fit that data, but you try to extend it into X-rays, ultraviolet emission, radio waves. Models have different predictions, so you want to extend into multi-wavelength observations to try to pick out the right models. So even more so, if you can extend into what neutrinos would be emitted or what gravitational waves you would see, it's a way of constraining and picking out the right models. So it's an important thing to do. Any more information you can get. So if you're stuck here observing from a great distance, you want all the controls you can get on theorists. And I admire the theorists, and I'm not criticizing them, but they need to be constrained to get the right model. So back in 1987, I had the job of getting the mailed-in copies of IU circulars, because we were heading soon, we thought, it turned out to be 4 years later, of the launch of Gamma Ray Observatory. And we could look at more things of this gamma ray burst, other X-ray transients, pulsars, and we don't know what the state of the universe was. Of course, years earlier, they would come by teletype. Anybody here ever attach a teletype to an old S100-based system? You ever used a teletype? Quite a mechanical device. Well, anyway, by this time, they were being mailed to us in clumps. And there are just dozens and dozens of supernova cards. I just go through the supernova, threw them away. Well, I missed this one. This is an important one because there's, whoops, go back here. A supernova in the Large Magellanic Cloud is only 150,000 light years away from it's a irregular galaxy going around the Milky Way. I got chastised for missing this. We read about it in a newspaper a couple days later. Terrible thing. And so we're very sorry we missed this. We would hope to have the Gamma Ray Observatory, but would have great data from all these experiments. If we were only 4 years later, we would have seen it. We were stuck with trying to do something. We thought we were not going to be all involved in trying to make any of these measurements on the supernova. We hope to see the decay of nickel-56, cobalt-56. There's some lines of radiation, 847 keV, 1238 keV. And we were very gloomy because we thought, well, we were out of the picture. We couldn't make any measurements. But then we got a call from Lockheed Martin scientists, Bill Sandy and George Nakano. And they had an instrument that flew on a U-2, a germanium detector, very high spectral resolution, be perfect for looking for these lines. They actually were looking down, swinging back and forth to look for lines from the various sites that would exist in the USSR to look for nuclear activities. And of course, I don't know how they got permission to take this very important device and put it on somebody's balloon, but they did. So they first of all called up Goddard Space Flight Center. I think it was the Egret experiment. Carl Fichtel said, could you put together a pointing system for us? They said, no, we're too busy getting ready for GRO. We can't do it. So a little bit later, they called Jerry Fishman, my boss at NASA, said, we need a pointing system. He said, sure, be glad to do it for you. So he pulled everybody off but one person on BATSI, and we focused on building a system. We hadn't done this for 10 years, but he said, sure, we can do that for you. Very bold move. So after 3 months, this is a system we put together. You can see it looked a little bit chaotic here, but it's built in-house. On the left side, we actually attached some of our BATSI detectors. You can see somebody saw the last talk, see the truncated cone here with the PMTs on the back. We don't see their detector. This is the frame it was to be mounted in with lead bricks to simulate their weight and all the electronics. I worked on the pointing system software for that. So the first system was a disaster. So we have a magnetometer look at the orientation of the balloon. They had about a 6-degree field of view. We need to point the thing within 3 degrees of the right direction. And balloons are randomly rotating because they're being driven by the winds on the opposite sides of the balloon, this 300-foot diameter balloon. And they spin. It might take them an hour to go around uniformly, but then they might go back for a while in 20 minutes in another direction and move again. They're randomly rotating, and you need to undo that somehow. So our system was very simple, too simple. It was just a gear, a large gear, with a motor to drive it. And so when it turned away from the right direction, based on our magnetometer measurement, we turned the motor on and moved the gear back in the right direction. And we calculated the angular velocity just by differencing the angles we were measuring with the magnetometer. Well, it worked, in a sense, it worked like pumping a swing. We were better off to just turn off the system, let it randomly rotate. We spent more time pointing at the source with our control system off. It was a disaster. So we came back from the trip. We saw somebody from the systems control lab. Remember him doing a plot in one of the offices there, and he plotted omega versus omega dot, angle versus angular velocity, and with our control inputs. And he said, I don't see how that could work. Well, he nailed it. So he came up with an idea to use an angular velocity sensor, quick feedback, and a torque motor, which is something that can give a very quick kick with control authority to undo the rotation that was taking place. And I modified the software to handle that, and it was a great success. We controlled it with about 1/10 of a degree accuracy, and we went down for 5 flights. It was just oh, by the way, one thing that was going on at that time, so we were spending years writing requirements documents, test plans. It's all in a virtual world of paper, And meanwhile, our compatriots, other areas, were building experiments, flying things, getting data, publishing papers, and we were just sitting there in a paper world. It was a very depressing time. It was testing phototubes years and years and years. So it's just a great relief. We actually could go do something, make some measurements, and get some papers. So it was a great relief to the team to go do that. So after these flights, so I'll show the results first. So we actually, because it wasn't our results, it was the Lockheed results from their experiment. You can see these 2 lines here, 847 keV and 1.226 MeV. And here's a blow-up of the 1.238 lines. So we were the first ones to measure these lines from the supernova. Very thrilling. But what was happening was there was Jerry Scher of Naval Research Lab. He was the principal investigator for Solar Maximum mission, which has been up for about 5 years. And that system pointed always at the sun. But as the Earth rotates around the sun, it spends some time pointing in the direction of the LMC, Large Magellanic Cloud. And so they were hoping to get something from their shield and make a measurement. So every few weeks, Jerry Scher would call my Jerry Fishman, say, are the lucky guys seeing anything? And Jerry held him off for a long time. But finally, Jerry says, yes, they're seeing something. At that moment, they dropped their pre-written paper into Astrophysical Journal, and they got the credit for being the first one. They published first based on that phone call. Hey, we like Jerry Scher, but not quite as much after that. So the other thing you expect to see from the solar supernova is neutrinos. When you have all the protons and electrons joining each other to become neutrons, they emit neutrinos. They were first hypothesized by Wolfgang Pauli in 1930 to explain energy conservation, angular momentum and energy conservation, a missing particle. Detected in 1956 by Cowan and Reines. Frederick Reines won the Nobel Prize in 1995. He actually came here to UCI. He was the founding dean of the Department of Physics here at UCI. We learned later, based on some measurements made by Ray Davis, that looking for solar neutrinos, that they weren't as many as expected, that they actually have different flavors, different types of neutrinos, electron, tau, and muon neutrinos, which change between each other over time. They're very unreactive. Their mean free path, the distance over which half of them interact, is 1 light year of lead. 1 light year of lead. I mean, that's an impressive amount of material. And the expected flux from the fusion reaction to the center of the sun, right here where we're standing, is 10 to the 6th per square centimeter per second at the Earth, going through this all the time. Doesn't matter, they don't interact with us. So Ray Davis got the Nobel Prize in 2002 for making that discovery. It was back when I was in graduate school, people were very puzzled. He got better and better statistics and wondered why such a small number, until it was realized the ones that leave the sun of one type change to the other types. You only see only 1/3 of them get measured. So the experiment only can measure the one type of muon. So there's an experiment that was built in Japan to look for decay of the proton, which turns out they don't decay, so they didn't measure anything. But they upgraded to look for solar neutrinos in 1985. It's a huge facility, 6,600 photomultiplier tubes, to look for Cherenkov radiation when something hits a charged particle, and that leaves energy in the detector. And so what they end up discovering is they actually had some interactions of neutrinos with the water particles, the protons in the tank. And also there was an IMB experiment, Irvine, Michigan, Brookhaven experiment, which also made some measurements. This came here just 2.5 hours before the supernova was detected. They had these measurements of neutrinos. Now, this isn't the number of neutrinos. This is just one by one. The white points are for IMB, and it's a time of occurrence. And this is the energy of the electron in MEV. So each of these points is a single interaction of a neutrino with an electron. They leave as much as some of 40 MeV. So I think there were 8 by one, 11 by the other. It's on the next slide here. Very tiny number detected. Yeah, so there are 11 interactions at Kamiokande and 8 at IMB, about 2.5 hours before the optical detection. So this confirmed that it was a type 2 supernova event. So we have all these understandings and models and theories for many years. This is what's happening. Massive stars, use all their fuel. Iron interacts with gamma rays. Neutrons are formed. But it's all valid theory. But this is the first measurement ever made showing that actually was actually occurring. So it's always good to have actual data. So now I'll turn to, let's see, I'm reading for time here. This might be a good place to stop for a break. So I'm going to talk here about LIGO, the Laser Interferometer Gravitational Wave Observatory. It first went into operation in 1999. The 3 prize winners now, Kip Thorne, Barry Barish, which I discovered just recently. He's now gone to UC Riverside, my alma mater. I think it's kind of amazing. His son was at UCR already. It's a family thing. It's kind of surprising he went there. It took 40 years of technology development and funding. Somebody asked me what the funding was. I'm sure by now it's over $1 billion. It was paid for by NSF. It's hard to struggle with annual budget such a long time to convince people to do this. So it's probably the achievement financially is just about as important as achievement technically to accomplish this measurement. It's a 4-kilometer long vacuum chamber with 40 kilogram mirrors, 100 kilowatt infrared lasers, and mirrors cooled to microkelvin. So it's amazing. Somebody gave here a talk about 2 years ago who's a member of the LIGO development team. Might be good to get them back someday. I'm just going to gloss over all the technical aspects. It's done with the interferometry. They send a laser beam to a beam splitter, this half-silvered mirror, and they send half of it down one line, 4 kilometers and back, and half the other way, recombine it and send it to a detector. And it's done in a way so that they're out of phase. So if there's no movement of the geometry of space, then they cancel. I'm going to show a short video by Ray Weiss here explaining that.
To measure the stretching and squeezing, Ray turned to a device called an interferometer. A laser beam is split and sent down a pair of long perpendicular tubes, each precisely the same length. The 2 beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
and you add them together, you get nothing. You get a zero, a big fat zero. No light gets detected at the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
The light takes longer time in here than it did in this arm. Now it takes a shorter time, and these things don't cancel so beautifully anymore.
So they're located in Hanford, Washington, and Livingston, Louisiana. And there's a new one operating in Italy called Virgo. And this year, I just saw it recently in Nature, in Kamioka in Japan, which is close to where the Kamiokande device was, which measured neutrinos, was located. You can't get the directions to these sources very well. You're just doing the time delay. It's like the same problem with getting a circle in the sky that was showing you for finding locations towards gamma ray bursts. So the more detectors you have, the better you can locate the direction towards the source. So the sensitivity is amazing. You can measure the mirror displacement of 10 to the minus 19 meters, 1/10,000th of the size of a proton. How can you possibly do that? Well, first of all, you're cooling the mirror. You don't have a lot of thermal vibration of the protons. And you're looking for the center of mass of the mirror. You're getting the mean position of all the objects in the mirror. So that's better than you can do in any one item. But that's a remarkably small amount. You're trying to answer the question, do the actual signals they get from black hole binary mergers or neutron star mergers behave according to general relativity? They take it, wiggles according to the signals they get from the detector and the interferometer, and they model what the masses would be behaving based on the general relativity equations. Do they match the wiggles they see that they measure? And that's how they do the fitting to come up with a measure of what the masses were. There's a lot of different inputs cause noise here. Farming activities, molecular vibrations, everything. They have to remove all the things. So they're looking for things that happen in common with the appropriate time delay. They need a signal that occurs in Washington, Louisiana, with appropriate time delay be consistent with some signal traveling at the speed of light in order to remove them. But it's a very complicated process. They introduce test signals into these systems unbeknownst to the experimenters to see if they can actually find the signals. They're constantly struggling with challenges to see if they're finding the ability to find signals in all this massive noisy data. So this is an example of a plot of some of the noise things processes they have to worry about. So they're trying to look between about 20 hertz and a kilohertz. So some things aren't so important, like seismic noise, as you might imagine, earthquakes, drops off. You don't have shaking unless you have a rattle in your house. You don't have high frequency signals from earthquakes. And gravity gradients, you just have the different heights in the chamber. That isn't important. The ones that are important are quantum noise, which is shot noise, photon counting noise, and radiation pressure. You're bouncing photons in the laser beam off the mirror that introduces noise. You can't avoid it. And then the coating on the mirror has thermal processes. You have things hitting a few atoms still left in the vacuum, high vacuum, but it's not perfect. So you have things hitting the coating and giving noise. So the overall noise is actually very low. It's strain of 10 to the minus 23. I looked at the original paper in Physics Today, just highlighting they're about to go into operation in 1999. And they're more of an order of magnitude higher. So in the last 20 years, they've improved by more than an order of magnitude. They've reduced the noise by more than a factor of 10. Which is always good, looking for weak signals. And so in 2015, September, they made their first detection of a merger of two massive black holes, 30 and 35 solar masses. And by looking at the amplitude of the signal, they come up with the distances, about 440 megaparsecs. This wasn't announced right away. They studied this, fit this, discussed this among themselves. I think it was announced about a year later. Very exciting result. You can imagine the planning. Well, as I say, it went for 40 years. So it's very exciting to actually, the people that look for proton decay, they never got that success story. So it's very, very good, very, very exciting achievement. So, yes?
How do they figure the distance
They figured the distance to the thing by the amplitude of the measurement. You have one of our R² effects going on. So by looking at the amplitude of the wiggles, by the displacement of space-time, they can figure out the distance to the source by 1 over R².
But they'd have to know the mass, right?
Well, they get the mass. They're looking at they understand the mass because of the rate of change of how they're combining. So they get the mass. They fit the mass by the rate of change of the signal. They know how much mass. Actually, of course, when you measure the mass of the inspiraling particles or masses, black holes, some of the mass is lost through gravitational radiation. I think about 3 solar masses is not in the end result. It's lost by gravitational radiation. So the mass they get from the inspiral rate and the amplitude of the signal tells them how far away it is. So on December 3rd this year, they released a catalog. They have 10 black hole mergers. This one here as much as 50 solar masses and a 35 solar mass object. And you see there's one trace here that's more interesting, it's much longer. They actually detected a binary neutron star merger, which is coming up to talk about that. That's actually pretty exciting in terms of what you might see beyond just the black hole merger. So there's a paper now by Nobel Prize winner George Smoot. He was involved with measurements of the cosmic microwave background radiation. So when somebody comes out in opposition to your results, and he's a Nobel Prize winner, your ears perk up and you pay a lot of attention. So this is probably very disturbing to the LIGO team members. What is gravitational lensing? If he says gravitational lensing is affecting their results, if you have distant source S, but it's radiation, either gravitational wave radiation or light radiation, whatever, passes close to an intermediate, very massive object, say another large galaxy, it bends the light. We know this from measurements that were made in the 1919 solar eclipse that sort of established Einstein's idea how light was affected by gravity was confirmed. So it's something that's been very well established that gravity affects light. Whoops, sorry. Okay. So if it passes on one side of the object, it tends to bend in this direction. On this side, it bends the other direction. Of course, we think the light is unaffected. That's our first inclination, to trace it straight back from where it is last traveling. So we think we see two different sources. And the light travel time can be different. So these two systems, two binary black hole systems that arrived, 5 days apart. And Smoot is saying these are actually the same event that took different pathways to get to us. He shows the phase of arrival is identical. This isn't the first time he wrote a paper. I actually see some archive papers from about a year ago. So this is something that's been in the works for a while. And what also happens is you don't just see a time displacement, it can be magnification. This is a well-established phenomenon. There's certainly some of the Hubble images, they use gravitational lensing to actually see further into the distant past by using those features. They aren't perfect lenses. They tend to produce sloppy images or arcs and so forth. You have to model the nature of the intervening mass to form a good image. But it's a well-established fact that gravitational lensing does occur. And Smoot is surprised at what large masses are getting. And the claim is the masses are being affected by this gravitational lensing. And so this is what happens in science. You have two different viewpoints of how to explain the data. And this is going to take some time to ferret out. It's not really clear at this point. The LIGO people say there's other parameters than just the frequency of the inspiral. There's other things they can measure, and they claim to have data that shows that it's only a 2 standard deviation result. They think this is not well established, but this is going to be debated in the literature and at meetings for quite some period of time. So it's an open issue right now. So that this story has not been completed. So as I said, there was a neutron star merger, very exciting result. And what happened was, within a short time, namely 2 seconds later, a gamma ray burst was detected. This is a very complicated slide. I'll take my time explaining it to you. So this is a time axis down here. T0 is when the black hole merged and there's no more signal. It's when the frequency of the inspiral is changing. So it gets very, very rapid until it is done. There's only one black hole when it's merged. There's no more signal. So that's t equals 0 right here on this axis. This is a logarithmic scale, so it goes all the way up to, I put a line at 1 day and 10 days. So first of all, you need to ignore, so there's a gamma ray burst. Every other weak burst is measured by the gamma ray burst monitor on Fermi. I actually worked on that in testing phase. It was launched after I retired, but it's nice to see it get involved. It actually got the Rossi Prize, the highest prize in high energy astrophysics division, by the person now the principal investigator, who actually started as a co-op, Colleen Wilson Hodge, no relation. Nice to see a woman advance to that position. So that was a burst that happened. So this right away says that the gravitational waves travel at the speed of light. This is a very small offset. I forget right now what the distance is to the object, but it's millions of light years away. So 2 seconds out of millions of years. This is a very small offset in the time. Plus, there may be some process going on at the source that causes that delay. It may be an intrinsic delay taking place at the source. So, did it again. Okay. Ignore all these vertical bars. What these vertical bars are the times of the gamma ray burst coordinate network messages. It's kind of like IU circulars, where people are notifying people about what they've seen or even what they haven't seen. They're just communications among the astronomers. They don't say anything about measurements. So all the vertical bars, please don't look at them. Okay, so this is data from gravitational waves, gamma rays, X-rays, ultraviolet, optical, infrared, and radio. So the gravitational waves end at t equals 0. Gamma ray bursts came 2 seconds later. Then X-rays come much later, about 13 days later. UV came before that. Optical about the same time. There's some optical spectra, 1.2 days, 1.4 days, 2.4 days, showing changes in the spectra. This is 400 nanometers to 2,000 nanometers. Infrared, and then radio comes much later. So it's very complicated. But the point is, unlike all the black hole mergers, there was no signal in the electromagnetic spectrum. But now we have something associated with the merger of two neutron stars. We have something that wasn't consumed into the black hole that presumably was produced when these two neutrons have merged. We have the emissions. There's a kilonova produced. There's the emissions. There's hot environment, very hot because you're producing gamma rays and X-rays. There's a complicated environment in the vicinity just outside the area that is consumed by the newly produced black hole. So you might want to do that. Yes?
Now, if you look at the two black holes merging,
Are you talking black holes or neutron stars?
well, I think you do either one. Now, when they merge, there has to be some kind of a ringing effect that you can see on the other side of
Yeah, in the tail, so he's asking, is there some ringing that takes place after the black hole merger? There is. It's very quick. It's a very hard thing. And a lot of what takes place in terms of after the merger is taking place inside the event horizon. So there's not much taking place in the exterior. If you look, I don't want to step back right now, but if you look at the end of the signal measured by LIGO, there is a tiny amount of ringing, but it's not substantial, and it's gone in certainly less than a second. It's very quick.
But my question was, might that not modulate the beam where you could actually see it, or is it just too small? You know, it looked like the beam might be modulated by that ringing.
Well, as I say, the signal you see from the interferometer, there is a very slight amount of signal when the signal comes to an end. There's a very slight amount. It's very high frequency and it ends very quickly.
That's what I'm talking about. No, that's too faint to then modulate the beam of any kind where you might be able to see that.
Are you talking about the beam in LIGO?
The gamma ray.
Oh, yeah, no, right. Well, see, the gamma ray signal comes 2 seconds later. That's all done, said and done, before the gamma rays even start. There's a 1.7 second delay before any gamma rays are emitted. That's all done before the gamma rays come out. There's nothing available to show you that modulation. Okay. Another question? No? Okay.
Every day or two, on average, satellites detect a massive explosion somewhere in the sky. These are gamma ray bursts, the brightest blasts in the universe. They're thought to be caused by jets of matter moving near the speed of light associated with the births of black holes. Gamma ray bursts that last longer than 2 seconds are the most common and are thought to result from the death of a massive star. Shorter bursts prove much more elusive. In fact, Even some of their basic properties were unknown until NASA's SWIFT satellite began work in 2004. A neutron star is what remains when a star several times the mass of the Sun collapses and explodes. With more than the Sun's mass packed into a sphere less than 18 miles across, these objects are incredibly dense. Just a sugar cube-sized piece of neutron star can weigh as much as all the water in the Great Lakes. When two orbiting neutron stars collide, they merge and form a black hole, releasing enormous amounts of energy in the process. Armed with state-of-the-art supercomputer models, scientists have shown that colliding neutron stars can produce the energetic jet required for a gamma-ray burst. Earlier simulations demonstrated that mergers could make black holes. Others had shown that the high-speed particle jets needed to make a gamma-ray burst would continue if placed in the swirling wreckage of a recent merger. Now, the simulations reveal the middle step of the process, how the merging star's magnetic field organizes itself into outwardly directed components capable of forming a jet. The Damiana supercomputer at Germany's Max Planck Institute for Gravitational Physics needed 6 weeks to reveal the details of a process that unfolds in just 35 thousandths of a second. The new simulation shows two neutron stars merging to form a black hole surrounded by superhot plasma. On the left is a map of the density of the stars as they scramble their matter into a dense hot cloud of swirling debris. On the right is a map of the magnetic fields, with blue representing magnetic strength 1 billion times greater than the Sun's. The simulation shows the same disorderly behavior of the matter and magnetic fields. Both structures gradually become more organized, but what's important here is the white magnetic field. Amidst this incredible turmoil, the white field has taken on the character of a jet, although no matter is flowing through it when the simulation ends. Showing that chaotic magnetic fields suddenly become organized as jets provides scientists with the missing link. It confirms that merging neutron stars can indeed produce short gamma-ray bursts. At this moment, somewhere across the cosmos, it's about to happen again.
So I showed this slide before where theorists speculated that neutron star mergers could be the source of the short burst, so now that's been confirmed. So, progress. I showed you that was a very weak gamma-ray burst, so we think we were viewing that from not the core of the jet, but off to the side. When I showed those movies before about the jets being expelled from the collapsing massive star, a different case in this neutron star merger, you can see the core was at very low density, but the densities are small enough that you can deviate from the central core and still get gamma rays out, and that would be true in this case as well.
Gravitational waves have the potential to unlock so many secrets of the universe, and perhaps most excitingly of all, going back to the beginning of time at the start of the universe and the Big Bang. 100 years ago, Einstein presented his miraculous theory of general relativity, and one of its greatest predictions, gravitational waves, has been a holy grail of scientists for the last 100 years.
Is the reflected beam?
We built the most exquisite instrument on Earth, a large-scale project involving 1,000 scientists and many billions of dollars, and a year ago we announced the first detection of gravitational waves from a binary black hole system, a cataclysmic event in space. This time we detected the collision of two very dense stars called neutron stars. These are the densest type of stars that we know of. With this discovery, we have the opportunity to learn so much more about neutron stars, which have been quite a mystery to us. Unlike black holes, they give off other signals as well in the electromagnetic spectrum, and following this detection, our astronomy partners searched that region of sky for these counterpart detections.
So SkyMapper was on that source, on that event, as soon as night fell over Australia. And it was the first telescope to report the colors of the fireball that we saw emanating from that explosion. And it was much hotter than what we expected from previous calculations, which is interesting because we can now really learn about what neutron stars are like and how these collisions happen. So we think that these neutron-star collisions are the sites where rare, heavy, precious metals like gold and platinum and other exotic materials are formed. And many of those materials we find on Earth today probably were formed in a neutron-star collision way before the Earth formed itself.
If you go back to my first lecture when Burbage, Fowler, and Hoyle came up with the nucleosynthesis of elements in massive stars, everyone thought that most of the elements were made by the slow process called S process, and in the supernova itself, all the other elements were made in the R process. So now we've recently learned that's not the case. Many elements are actually made in the kilonovas that take place in the vicinity of neutron star mergers, so they're a critical part of how this world came to be. This is a fairly excitable astronomer, so I thought I'd show that to show there's some humanity within the domain of astronomy.
I'm Andy Howell. I'm an astrophysicist at Las Cumbres Observatory and a physics professor at the University of California, Santa Barbara. Normally on Science vs. Cinema, we review the science in movies, but this time we have breaking scientific news out of my observatory. It's about the discovery of a new astrophysical phenomenon called a kilonova.
Sure, most of you have heard about gravitational wave detectors. These are the LIGO detectors in Washington State and Louisiana. About 4 kilometers long each arm. They're two identical instruments, and their purpose is to measure the passing of gravitational waves through the Earth. Gravitational waves are distortions in space-time.
On August 17th, the two LIGO detectors in the United States and the Virgo detector in Italy measured the distortions in space-time coming from a gravitational wave passing through the Earth. NASA's Fermi satellite detected gamma rays coming from the same direction in the sky. These signals were unlike anything we'd ever seen before, but they were exactly what was expected from the merger of two neutron stars, producing a catastrophic explosion called a kilonova. These are solid stars, harder than anything you can imagine, and they're like a giant atomic nucleus, only one 10 miles wide and more massive than the sun. They're composed entirely of neutrons. They're almost black holes, but not quite. The problem is, by astronomical standards, these explosions are faint and fast. As a result, astronomers had never seen one. So we get this alert from LIGO. And then what happens?
Right, so they send us this localization region in the sky, which was about 30 square degrees big, and they say, you know, the event happened somewhere in here, but we don't know exactly where, which is why we had prepared this software in advance that would figure out what galaxies in those 30 square degrees we should be looking at first, based on their mass and distance, and then sends that information to the telescopes, and the telescopes start looking at these galaxies one by one. Lucky for us, galaxy number 5 on our list was the one that had the explosion in it. There were like 5 other groups that were looking at the same galaxy as we were in the same span of 45 minutes. And then we all started sharing our information about what we had seen happen there.
Even satellites in space got in on the action, like NASA's Swift satellite and the Hubble Space Telescope. Ground-based telescopes were at a disadvantage though. The explosion was only visible for about an hour at the start of the night. You'd then have to wait 23 hours to see it again from the same telescope. Getting around that limitation is exactly why we built Las Cumbres Observatory. It's a robotic network of telescopes placed all around the globe so that there are always telescopes in the dark. These icons represent where we have telescopes. When we first discovered the explosion, it was over Chile. But then, as the Earth rotated, we picked it up again over Australia. And then, 8 hours later, we saw it over South Africa. In the 24 hours that the Earth takes to rotate, we can observe the explosion 3 times with our network.
So this is the initial light curve. It has some of the data. There's still some more we can extract. Do you want to see it?
Yes, let's see.
Like that is one day.
Over the next few days, we saw the explosion fading really quickly. It's the kind of observations you can only make if you have a global network of telescopes.
So do you have the latest spectrum?
Nope. I've never seen anything like this before.
Yeah, that is weird.
You know, you can then usually read off what elements are in there. I mean, we're all pros at this for supernova. We just look at the spectrum and say, oh, look, there's calcium, there's silicon, there's whatever. But this damn thing, You don't know what the velocities are, and we don't know what the elements are, because it makes weird elements. And it's full of damn neutrons or something. I mean, what the hell does that look like when you make fusion inside of a ball of neutrons? Astronomers have long theorized that two neutron stars smashing together would synthesize heavy elements like gold. In fact, your jewelry was probably made in an explosion just like this, in some kind of cosmic alchemy. Using this data, we can probe extreme conditions not possible on Earth. We can test Einstein's theory of relativity in new ways, and we can finally solve the riddle of how the heaviest elements are made. It's hard to explain to people how this is such a different kind of discovery than we've ever made before.
Right, because until now, almost everything we know about the universe we've known through light. For the last 500 years since the telescope was invented, that was our only way to study the universe. So it was like we were only seeing the universe, but we couldn't actually feel or hear it until these gravitational wave detectors turned on. And now, for the first time, we have both gravitational waves and the light from the same event at the same time. And that is really not just a new discovery, but it's a new way of making discoveries about the universe.
We felt the universe shaking from two neutron stars merging together. And then we had smart, fast telescopes that allowed us to watch the explosion while it was still going on. And it's only possible because we have new technology. Anytime you can see the universe in a new way, you're gonna make new discoveries. This one really blew our minds.
So this is quite an interesting plot here showing what the sources of the elements are from many different places. So the hydrogen and helium take place in the early universe when there's a high density, and before there's any galaxies, they're close enough together and hot enough they form hydrogen and helium. Then you have some lithium produced, but in the cosmic rays interacting, they actually cause fission. A lot of things happen in like dying low mass stars. That's like what happens in our sun. It produces white dwarfs, so it's very spotty. But then a lot of them are happening then in this merging neutron stars. Look at all the yellow here. One especially interesting case is iodine. Most of the iodine produced in the universe, a small fraction comes from dying low mass stars, but most of it comes from merging neutron stars. And iodine is needed for life, so that's kind of interesting. Here's a plot I found for what is thought to be needed for life. And iodine is the only one that principally comes from merging neutron stars. So how many people think if there weren't any merging neutron stars that life wouldn't exist? I think what would happen is evolution would have found a different way. We'd be different, but probably life would still exist. So let's go back and talk about the broad range of gravitational wave astronomy. Right now, we have LIGO making measurements in the 10 hertz to kilohertz range, and that's from compact binary in spirals. But there's a broad spectrum. When I saw a talk by Kip Thorne here last year at the Rhinus lecture, he showed this plot. There's other ranges of frequencies we'd like to pursue that would give different information. So in particular, the LISA experiment, the laser interferometer space antenna, will show us heavier masses interacting, 10 to the 6th solar mass binaries. So that's the good news, but as you can read here, it's horrifying and not going to launch until 2034. I find that extremely disturbing. And then if you think about what's happening at the Big Bang, when all the mass in the universe is moving around, there ought to be a giant signal of gravitational waves from that event, or even from the inflation event that preceded it. But there's a lot of redshift, there's time dilation. These things take place on much lower frequencies. So 10 to the minus 10th frequency, that's one cycle in 300 years. So that's really, it's hardly a frequency. So you kind of, whoops, lost it. You explore that with pulsar timing. There's the European Pulsar Timing Array and the International Pulsar Timing Array. And for one thing, they don't really reach down to where you'd like to get in terms of sensitivity. And I also read that they've been operating this for about 4 years, I believe, and they're only operating at about 10 to the minus 6 frequency. They're looking at timing of radio pulsars with microsecond accuracy. So it's going to be a very long time until they enter their range and they might hope to see something. But the grand view of gravitational wave astronomy is going to take a long time to reach the really interesting stuff, which is what took place in the early universe. Look how long it took astronomy and optical range to get to the current state. So it's kind of a 100-year project to get the full information, or to really increase the understanding that comes from gravitational wave astronomy, I believe. So now let's move back to neutrinos. The neutrino detectors we talked about in the past are sensitive to 10 to 20 MeV neutrinos, the kind you see from the sun or from massive stars imploding and producing neutrino blasts to the Earth. But there's other sorts of forms that could actually produce neutrinos. And there's a rather large cubic kilometer of ice in Antarctica that's been produced called Ice Cube. I remember seeing talks about that way back in the 80s about sensitivity. It seemed a dream at that point. It took a long time. They started building it in 2010, done in 2015. And it involves many different institutions, including UC Irvine. It detects much higher energy neutrinos, up to 10 to the 14th EV. There's different kind of processes that we're producing that. It only takes it took a lot of people to build it. It only takes 2 people to operate it, and they put their data on tapes and bring them back to universities and analyze them. They've been running for quite some time. That's just the color indicates the time of occurrence of the detection. There's big strings of photomultiplier tubes. I think I showed here's the plot that shows that. They have 86 strings. They drilled firmly all the way down to nearly bedrock, and they run strings of cables down with photomultiplier tube detectors on them, and for that data is transmitted up to the surface. Here's an example. They actually were built in Sweden, and that's the example of it actually lowering them down on a cable. They want to build them with very high reliability because you hate to have to extract a string to do a repair. So that's the example. You have a neutrino hitting a proton in the ice on part of the water molecule, and it produces a Cherenkov light because it's moving faster than the speed of light in the medium, and the photomultiplier tubes pick up the signal. And that's how the measurement is made. Well, after running for 5 years, this is a plot, a map of what they've detected. So this is galactic longitude, galactic latitude. And what you see is not a lot of sources. I think there's like 1, 2, 3, 4, 5, 6 really bright sources. And they're confirmed by measurements by other observatories. So these are valid detections. But I point out that there's over 2,000 known blazars. Blazars are active galactic nuclei with supermassive black holes at the center. And they're first seen in radio, radio jets. But they also are seen in gamma rays. So when they consume a lot of mass at the center, they're detectable in gamma rays, and they fluctuate in intensity. So there's a lot of blazars have been seen, but not a lot of them detected by this experiment. And you'll see why it's important coming up, in my opinion. So in September of 2017, the IceCube put out an alert. They found a single neutrino of 10 to the 14th EV, and they sent an alert out. Then the Swift X-ray telescope reported finding 9 sources of X-rays coming from the same area of the sky. Now, I'm not sure just how tight it is. I mean, one worries about random correlations, but they did find a signal of X-rays coming from the same area of the sky. And 2 days later, the Fermi Gamma Ray Space Telescope identified gamma rays coming from one of the same sources that Swift found. You're starting to see hints of something's going on in this region of space where they found a neutrino. But it's just one neutrino. So then a network of optical telescopes announced that this source had been brightening over the past 50 days. And another optical telescope found evidence the source is a blazar. Okay? And that was confirmed by the Very Large Array in New Mexico, a radio signal that it was a blazar. And so now, if that's a valid detection, then it may be that this source is a source of cosmic rays. Now, cosmic rays are first detected way back in the early 1900s, first on a mountaintop and then by balloon flights. They're very energetic particles. Because they're charged particles, you can't trace them to their source. And people have wondered for a long time. They thought first maybe supernovas, but that's been ruled out. What is producing the cosmic rays? So this is the latest version of maybe it's these blazars that are producing the cosmic rays. But what we have is one neutrino from one blazar. It's a little premature, I think, to say, well, that's it. That's the source of the cosmic rays. That's what the published paper is claiming. It is the case that I read in a recent paper that IceCube can be increased in size by a factor of 10, but only increasing the number of light detectors by a factor of 2. So they certainly need to increase their sensitivity. It's really hard to measure cosmic rays. To see there are people at Marshall Space Flight Center that put up a whole series of about 20 large area balloon flights in the range of about 10 to the 12th EV. They had you have only about 1 per square meter per second, or maybe less than that. You have to very long balloon flights, and many of them, to make a measurement. But look what the rates are up here, 1 per square meter per year. It's hard to do a balloon flight and measure that. Or how about up here, 1 per square kilometer per year? You cannot measure that from airborne experiments. This is an example of a cosmic ray. They interact in the top 100 grams, the first 10% of the Earth's atmosphere, and there's a big cascade of interactions. They interact with atoms and produce a cascade of particles, most penetrating of which are the muons that get all the way to sea level. We used to use muons in the sub-basement at Cal State LA to calibrate our gamma ray detector. They're very, very, very penetrating. So it's very, very difficult. So I'll put my conclusions here in the summary. So summary is that short bursts are caused by neutron stars. It's a flat statement that neutron star mergers are causing the short bursts that we've been measuring for so long. Finally, something concluded. Long bursts are likely associated with rare types of supernova, which eject narrow beams of superhigh energy particles of variable length factors, which generate gamma rays when they collide. That's the internal shock model. I say it's likely. Gamma ray bursts are beacons telling us of rare events taking place in the early universe. So we really can't say definitively it tells us a great deal about the early universe, but they certainly are something that come from very early as far as the redshift of 9. Gravitational wave astronomy will be a growing source of information about the universe and its constituents. It'll take a long time to reach fruition. And so neutrino astronomy is still in the early discovery phase and is likely to grow in importance in the years to come. Thank you.
We have time for questions. Any questions?
Yes.
Cosmic rays. Now, I think I read somewhere.
Start over.
I think it was Florida Institute of Technology that was doing research on lightning, and they have determined, I think it was, that lightning may be started by cosmic rays.
Yeah. Not in direct answer to your question, but I can tell you an interesting story about that with BATSI. So we were flying BATSI back in 1991, and we were looking for the locations of gamma ray bursts, and we started seeing signals coming from the Earth. This is back when Mount Pinatubo was emitting a lot of stuff into the air, and we actually discovered terrestrial gamma ray flashes, so that they're actually caused by upward moving lightning. Now, what induced the lightning, I can't tell you, but that was kind of, when you fly a new detector, more sensitivity, and a new range of energy, you do it for the focused idea. We're going to measure something. But quite often, you have things you never predicted that you measure. Now, as far as being induced by cosmic rays, we have a lot of cosmic rays deposited. They vary by way over the solar cycle, because Furbish decreases as solar activity goes up, it tends to reduce some of the cosmic rays. So there's things that are dynamic based on the solar cycle that would modulate that. So I would think you'd see a modulation by the sun's behavior as a way of deducing whether cosmic rays are involved. It's just one thought.
Interesting.
Any more? Yes. Right here.
Within the last couple of weeks, there's been news about these bursts of radio waves. Mm-hmm. Can you speculate what that is about?
I've been so busy preparing this talk that I haven't really had time to pursue that. I was afraid somebody might ask that question, so I haven't pursued that. First, I have to say that your radio photons are such low energy compared to gamma rays, you know. Not to poo-poo them, but I don't think I really know much about their cause or the distance scale. I do know that just prior to this year, there was only one fast radio burst that was known to be a repeater. And just within the last few months, I think, they found another one that's a repeater. So it's likely, so that's a rare event. So there's probably more than one cause for the fast radio bursts. But other than that, I really don't know the answer. Right.
All right. Bob, thank you very much for a wonderful series. We really appreciate your time.